In this video, we're going to go through an exponential functions test review, and we're going to go through 18 questions that are frequently asked on exams like this together. So go ahead and pause the video, see if you can do some of these problems on your own, and then you can check your work with what we're going to do here together. So let's dive into the first couple examples, which involve graphing exponential functions. So the first one, we've got f of x equals 2 times 3 to the x power. Now, notice that this is in the form y equals ab to the x power. Now, when you see that variable in the exponent position, that means it's an exponential function. This number here that's right below the exponent, this is referred to as our base. And remember, if the base is greater than 1, this is going to be an exponential growth function. The 2 is going to be a vertical stretch by a factor of 2. Let's make a table. Let's see what this graph looks like. You might want to just pick some easy numbers like -1, 0, and 1. Some teachers will have you do like 5 numbers, so you might want to do -2, -1, 0, 1, and 2. But a couple negative, 0, and a couple positive are usually pretty good. If we put -1 in, 3 to the -1 is 1/3, because remember that negative, you take the reciprocal, and then times 2 is going to give us 2/3. So that's going to be right about here. And 3 to the 0 is 1. Anything to the 0 power is 1. Times 2 is 2. Make sure you do the exponents before the multiplication. That's a common mistake that sometimes students make. And then if we put 1 in, 3 to the first is 3. Times 2 is 6. So right 1, up 6, right about here. Now notice that this graph is getting closer and closer to the x-axis, and that's going to be our horizontal asymptote. So I would draw that as a dashed or dotted line. Sometimes when it's on the x-axis like that, I like to put it as on a little bit of an angle just so that it stands out a little bit more. So now let's answer a few questions. So the y-intercept is this number right here where it crosses the y-axis. So that's going to be at 0, 2. If you're not sure, you can always put 0 in for x and then solve for y. That'll be your y-intercept. Now the domain, that's saying what can the x values be? Well, you can see the graph goes to the left forever and ever, and it goes up, but also to the right forever and ever. So the domain is saying what are the x values, and that's going to be all real numbers, or if you know about the interval notation, it's from -infinity all the way to +infinity. Of course, you can't reach infinity, so that's an open interval with the parentheses. The range is asking what can the y values be? Well, you can see it's not touching the x-axis, it's not below the x-axis, it's just above the x-axis. So we would say y is greater than, but not equal to 0. Or if you know the interval notation, you could say from 0 to infinity. Now the asymptote, the equation of the asymptote is this horizontal line. Remember, horizontal lines are y equals lines. That's going to be y is equal to 0. Remember, when you're working with functions in this form, you can think of it in a more general way, like ab to the x minus h plus k. This k value is what's going to shift that horizontal asymptote up and down. So if this is +2, it would go up 2. If it's -2, it would go down 2. But in this case, there's not a k value, so that means it's going to be y equals 0 right on the x-axis. Now this one here is referring more to what we call the end behavior. So the limit as x approaches infinity. That means as we go to the right. F of x, that's referring to the y values. Those are going up, up, up to +infinity, or you could just say infinity. But the limit as x approaches -infinity, that means the left end behavior as we go to the left, what happens to the y values? They get closer and closer to 0. So it's a limit. It doesn't actually reach 0, but you could say that it's approaching 0, okay, as you go to the left. Now for number 2, we've got a little bit more going on here. We've got f of x equals -3 times 1/2 to the x minus 1 plus 2. So how would you graph that? And can you answer these questions? Well, let's go ahead and make a table, but what I'm going to do is I'm going to focus in on just this part of the equation right here in my table, and then I'm going to do some transformations, okay? So actually, let's even do it a little bit even simpler. Let's just focus on 1/2 to the x power. So I'm going to do -2, -1, 0, 1, and 2. So when you put a negative exponent, that tells you to take the reciprocal, so that would become 2, and 2 squared is 4. 1/2 to the -1, you take the reciprocal, that's just going to be 2. Anything to the 0 power is 1. Anything to the first power is itself, and then 1/2 squared is 1/2 times 1/2, or 1/4. Now the negative is going to reflect it over the x-axis. It makes all the y values the opposite sign. The 3 is going to be a vertical stretch by a factor of 3. And what that's going to do is it's going to multiply all these y values by -3. So this is going to become -12, -6, -3, -3/2, and -3/4. Now the -1, notice is grouped with the x. When it's grouped with the x, it's going to have the opposite effect. So the -1 is actually going to shift the graph right 1. So that means I'm going to add 1 to all our x values here. So -1, 0, 1, 2, and 3. And then the +2, that's going to shift the graph up 2, which is going to affect our y values. So I'm just going to add 2 to each of these y values here. Okay, -3/2 plus 2 is 1/2, and -3/4 plus 2 is 1 1/4. Okay, now notice, I'll just cross out these old values, that this 2 here, this k value, just like we were talking about over here, that's going to be where our horizontal asymptote is. So that's going to be right here at y = 2. So we can answer that question. And let's plot these points. So -1, -10, that's kind of, let's see, -1, -10 is way down here. Let's do 0, -4. That's right about here. 1, -1, that's right here. 2, comma, 1/2, that's going to be right about here. And 3, 1 1/4, that's going to be right about here. So you can see that the graph is going something like that. Okay, now let's answer some questions. So domain, what can the x values be? Well, it's going to the left and the right forever and ever. So the domain would be all real numbers. You'll notice these exponential functions, the domain is always all reals. Or if you know the interval notation, it goes from -infinity all the way to +infinity. The range, the y values, it's below this horizontal asymptote. So we're going to say y is less than 2. Or if you know the interval notation, it goes from -infinity to 2, not including infinity or 2. And then the limit as x approaches infinity, that means as we go to the right, what is the y value approaching? Well, it's approaching 2, this horizontal asymptote of 2. And the limit as x approaches -infinity, as we go to the left, you can see the y values are going down towards -infinity. And then the y-intercept, we found out that that was -4. And you can figure that out by putting 0 in for x into the equation, but it just happened that we were able to find that as one of our points. So let me erase the whiteboard. Let's get into the next group of problems. Okay, for example, number 3 and number 4, we're going to write an exponential equation in the form y = ab to the x power given 2 points. So same thing for number 4, same instructions. So see if you can do these 2 on your own and we'll go through them together. Now for number 3, this one's a little bit easier because see how x is 0? So what I'm going to do is I'm going to put 5 in for y and 0 in for x. So that's going to give us 5 = ab to the 0 power. Now I'm also going to write an equation with this point. I'm going to say when y is 80, x is -2. So whenever you have 2 variables, you need 2 equations to solve that system. So here, this one, b to the 0, anything to the 0 is 1, times a is a, so we've got a = 5. Now I can take that 5 and put it into this second equation to help us to solve for b. So let's go ahead and do that. We've got 80 = 5 times b to the -2. If I divide both sides by 5, that's going to give us 16 equals b to the -2. And if I just want to solve for b, I could raise both sides to the -1/2 power. Now, why am I doing -1/2 power? Well, because power to power you multiply, that'll give us 1, and that'll give us just the b by itself. Over here, the 1/2 power, I know that's the square root. If it was 1/3, it'd be the cube root. So the denominator is the index or the root. Square root of 16 is 4, but that negative tells us to take the reciprocal, which means that this is going to be 1/4. Now we've got our a and b. Let's plug those back in and write our equation. So y = 5 times 1/4 to the x power. So that's our exponential function. If you want to check your work, which I recommend, you can go ahead and plug 0 in. You'll see that you get 5 for y. And if you put -2 in, you'll see that you get 80 for y. So you can double check your work a little bit. For number 4, same idea, same instructions. We want to write this exponential function. How would you do that one? Well, again, we're going to have to write a system of equations. So let's start off by saying when y is -9/2, x is 2. And over here, when y is -1/6, x is negative 1. So we have to solve that system. Now, here what you might want to do is, let's go ahead and rewrite this a little bit. So b to the negative 1, that's like taking the reciprocal or moving that to the denominator. Okay, and then over here, if we, let's just take this one step further. So let's go ahead and solve for a. So if I multiply both sides by b, you can see that a equals negative 1/6 b, or you could say negative b over 6. I'm going to plug that into this equation here, just doing a substitution. So this is negative b over 6 times b squared. 6's and b's kind of look alike, so that was probably not the best choice of numbers, but this was going to give us negative b cubed over 6. And let's go ahead and multiply both sides by negative 6. And so that's going to cancel. That's going to make this b cubed equals, let's see, this is 54 over 2, which is 27. And if we take the cube root of both sides, we can see now that b is equal to 3. Okay, that's great. Now let's plug the 3 back in here to solve for a. So that's going to be negative 3/6, which is negative 1/2. Okay, now we have our a and b. Let's put our equation back together. So we have y equals negative 1/2 times b, which is 3, to the x power. Now again, if you want to check your work, plug in 2, and you get back the negative 9/2, and if you plug in negative 1, you get back the negative 1/6. So let me erase the whiteboard. Let's go into the next group of problems. See if you can pause the video and do these next 4 problems. For 5 and 6, we're solving for x. For 7 and 8, we're determining whether the table represents an exponential function. So for number 5, what I would do first here is I'd divide both sides by negative 4. Kind of working from the outside in towards that variable there. So that's going to give us 1/2 to the x power is equal to 8, because a negative divided by negative is a positive. Now, what you can do is you can try to get the bases to be the same on both sides, and then you set the exponents equal to each other. So for example, 1/2 is like 2 to the negative 1 power, and 8 is 2 to the 3rd power. Power to a power you multiply, so this would be like 2 to the negative x equals 2 to the 3rd. Now that we have the same base, we can set the powers equal. So negative x equals 3, divide both sides by negative 1, x is equal to negative 3. Now you might recognize that right at this point, that if you take a negative, that's going to take the reciprocal of 1/2 and make that 2, and then 2 cubed is 8. But sometimes people like to get the bases the same and then just set the powers equal. That's called a one-to-one property of exponents. So what do you think for number 6? This one, you might recognize that this is actually just to the 4th power, because 2 to the 4th is 16 and 3 to the 4th is 81. So that one was kind of a simple one there, x equals 4. Okay, for 7 and 8, does the table represent an exponential function? Well, notice these x values, they're going up at a constant rate of 1. The y values looks like they're going up by 2 each time. And when you can see it's basically going up at a constant rate of 2. That's like the slope, like 2 over 1, 2 over 1, 2 over 1. It has a slope of 2. This is actually a linear function, not an exponential function. For number 8, what do you think about this one? Well, here it looks like we're multiplying by 1/2. Here we're multiplying by 1/2. Here we're multiplying by 1/2. Again, the x's are just going up by 1 each time, but we're multiplying by 1/2. Now, when you multiply by the same thing each time, with the equally spaced x values here, that's going to be an exponential function with base 1/2 in this case, because we're going up by 1. But the main thing is you're multiplying by the same number, that's exponential. If you're adding or subtracting the same thing each time, that's going to be linear. So this one would be more of an exponential decay function, because that base is between 0 and 1. If it was greater than 1, then it would be like an exponential growth function. Let me erase the whiteboard. Let's do the next group of problems. Number 9 and number 10, we have a couple of word problems. Let's see if we can read these and see if you can do these on your own. So for number 9, it says the value of a classic car is increasing by 10% per year. In 2009, the car was worth $20,000. Find the value of the car in 2025. So this is referred to as an exponential growth or exponential decay model. And equations in this form look like this. Y equals a1 plus or minus r to the t. Now the a represents like the initial or the starting amount. The 1 represents like 100%. And r is the additional rate of increase or the rate of decrease if it's minus r, and then t is the time, usually in years. So, and the y would be the ending amount. So in this case, it looks like in 2009, the car was worth $20,000. So that's our starting amount, or our A value. It's increasing, so this is going to be 1 plus 10%. Now you want to convert that percentage into a decimal by moving the decimal point 2 places to the left. So that's 0.10. And then I'm just going to put this to the t power. So what this looks like now, this is our exponential growth model. Sometimes they'll ask you additional questions like, what's the growth factor? The growth factor is this whole quantity in parentheses, 1.10. It's like you're multiplying by 110% each year. It's the original amount, 100% plus an additional 10%. That's the growth factor. But the growth rate, or the percent rate of growth, would just be the 10%. And so now we've got our model, and we want to know what's the car going to be worth in 2025? Well, that's going to be 16 years later, right? So that means that t is going to be equal to 16. Let's go ahead and plug that into the calculator and see what we get. So 20,000, 1.10 to the 16th. Okay, I'm getting an astounding $91,899.46. Now you want to round to the pennies, 2 decimal places, because this is money, and so that's how much the car would be worth after 16 years if it keeps growing at 10% each year. Now, what do you think for number 10? Same kind of idea. It says the value of a $2,000 bike decreases, okay, by 15% per year. Find the value of the bike after 5 years. Notice I'm just highlighting the key pieces of information. So going back to our exponential growth or decay model, we're starting at a value of 2,000. That's going to be our A. It's decreasing, so minus, by 15%, which move that decimal 2 points. That's going to be 0.15 to the t power. So let's just simplify a little bit here. So this is going to be 0.85 to the t. Now this is referred to as our decay factor. Our decay rate, or percent rate of decrease, is 15%. This is our initial amount, and t is a number of years. Now we want to know how much the bike's going to be worth in 5 years. Should be a lot less because it's decreasing. So 2,000 times 0.85 to the 5th power. I'm getting $887.41. So that's how much the bike is worth in 5 years. So let me erase the whiteboard. Let's go to the next group. For number 11 and number 12, see if you can simplify these expressions. And then for 13, 14, and 15, we're going to decide whether the function is growth or decay, the rate of growth or decay as a percentage, and the initial amount with these 3 functions. So if I was going to do number 11, remember the e represents our natural base e, or Euler's number, and you can treat it just like a variable, but when you multiply and the bases are the same, what do you do to the exponents? You add, so 2 plus 3 is 5, and then when you divide and the bases are the same, what do you do to the exponents? You subtract. You take the numerator's power minus the denominator's power. 5 minus 4 is 1, so this would be e to the first, or you could just say e. For number 12, when you have a power to a power, what do? You multiply, so that's going to be e to the 10th over e to the 3rd. When you divide and you have the same base, again, you subtract the exponents, numerator minus denominator, that gives us e to the 7th. Now for number 13, this is our base. Now notice this base is 2/3. It's less than 1, between 0 and 1. That means that this is an exponential decay function. So I'll just write decay. And the initial amount is this number here in front, this 3. That's when x is 0. Anything to 0 is 1, times 3 is 3. So we'll say initial amount, 3. And decay. And then the percent rate of decay. Well, this, how much less than 1 is this? This is a 1/3 less than 1. So we could write this as 1 minus 1/3. Or 1/3 as a decimal is about 0.33333, like that. Okay, so you can see that this is actually like a 33.3 repeating percent rate of decay. Okay, so you want to look at how much more than 1 it is or how much less than 1 and convert it to a percentage. Now for number 14, you can see that our initial amount is 20. I'll just write that down here. So initial amount, 20. Now notice this negative exponent. It's a little confusing because we see the 4/5, we might think, oh, that's less than 1, that's exponential decay. But we know the negative exponent tells us to take the reciprocal of the base. Okay, now you can see this is 5/4, that's more than 1. That means this is actually an exponential growth function. And the 5/4, that's like 1 1/4. That means that 1 1/4 is like 1.25. How much more than 1 is this? It's 0.25 more. Now, as a percentage, that's going to be 25%. So this is a 25% rate of growth. Rate of growth. Now, again, if they say what's the growth factor, okay, that's this 1.25, or what's the decay factor, that's this 2/3. But if they're saying what's the percent rate of growth or the percent rate of change, that's where you want to figure out how much more than 1 or how much less than 1 and convert to a decimal. Now for number 15, what do you think for this one? Initial amount is 12. So I'll just abbreviate, initial amount is 12. Less than 1, positive exponent. How much less than 1? 0.08. So this is definitely an exponential decay function. So exponential decay. 0.08 as a percentage, that's going to be 8%, right? So 0.08, you move that decimal 2 places to the right and convert it to a percentage. So let me erase the whiteboard. Let's do the next group of problems. Okay, see if you can pause the video and do these last 3 story problems involving compound interest as well as bacteria doubling. See if you can do these last 3 problems. And while you're doing that, I wanted to let you know that I've got 2 video courses for sale that I think will be of extreme help to you. Check those out in the description below. One is an Algebra 1 video course. The other one's an Algebra 2/College Algebra video course. One has 85 lessons, the other one has 87 lessons. And I take you through a typical course, to help you to master those topics. So check that out. Also, you can now become a member of Mario's Math Tutoring on YouTube. So if you join at the additional videos level, you can get access to a whole bunch of things, over 125 videos now. There's my full geometry course on there. There's ACT and SAT courses on there. There's midterm and final exam reviews as well. So check that out, as well as more videos that I'm going to be adding to that as we go. So check that out and become a member. So for number 16, what do you think on this one? It says a $4,000 investment at 5%, which is compounded monthly. Find the balance after 3 years. So the important formula that you want to memorize for this problem is A equals P 1 plus R over N to the NT power. P is the principal, or what you start with, that's the $4,000. 1 represents like 100%, like the starting amount. The interest rate is 0.05, and make sure you convert that to a decimal by moving the decimal point 2 places to the left. N is the number of times that you compound in a year. So monthly would be 12, weekly would be 52, quarterly is 4, semi-annually is 2. But remember, these N's are going to be the same, and then we're compounding for 3 years. So that's actually like 36 months that you're compounding. Now, let's see what this comes out to on the calculator. We've got, now you might want to make sure you use enough parentheses, or if you want, you can do the order of operations, start with the parentheses first. I'm just going to use parentheses. And then let's raise this to the 36 power. Okay, so I'm getting $4,645.89 if I round to the pennies, and that's how much you would end up with after the 3 years. Okay, so for number 17, this one's a little bit different because you're compounding continuously. Whenever you see that word continuously, you're thinking this formula right here, the PERT formula. A equals P times E to the RT power. Now, P represents the principal, or what you're starting with, the $700. E is your natural base E, Euler's number, about 2.7. R is the rate as a decimal, so that's going to be 0.08. T is the time, usually in years. And that's A is going to be our ending amount. So let's see how much you'll have after the 10 years. So 700, using my E key here, I'm getting $1,557.88. That's how much you'll have after the 10 years. Now for the last problem, number 18, we've got a bacteria is doubling every hour. There are currently 200 bacteria. How many will there be after 1 day? Well, we know 1 day, that's actually 24 hours. And we're thinking about a function that's like in this form right here, where A is the initial amount, that's 200 bacteria. B is our growth factor, in this case is doubling, so that's going to be 2. And it's doubling 24 times. So that's going to be 200 times 2 to the 24th power. Big number, we've got 3355, interesting looking number, 443200. Look, we've got 2 zeros, 2 4s, 2 5s, 2 3s. This is like a very interesting number. Okay, so that's how many bacteria you would have after 1 day. So great job if you're able to follow all these topics here. I've got more videos on each of these individual topics and more about exponential functions on my Marvelous Math Tutoring YouTube channel. So check out more videos there if you need additional help. Otherwise, good luck on your exam, and I'll see you in my other videos. I'll talk to you soon.